Hello, I'm Raviraj Saxena. I'm doing PhD in Department of Electronic System and Engineering under Dr. T. Prabhakar and Dr. Joy Kuri. I'll be presenting my work on IoT data management as a part of our Cisco Network Intelligence Scholarship. So I'll be working on the compression part as a or for the IoT data management part. So the motivation is that in the flights there are a lot of sensors are there, and we have only limited amount of storage for the flight data recorder, which is robust. So the per GB cost is very high for aircraft. Hence this necessitates the compression for storage for particularly for the longer flights. Now, in my work, there are two approaches we have investigated. One is dictionary-based, and the another is piecewise linear approximation. In the dictionary-based algorithm, we need to construct the dictionary, and the way of construction is the how we actually differentiate between the two algorithms. So one approach is the sparse PCA approach to construct dictionary, and another is the dictionary learning. And another algorithm is the piecewise linear approximation, where we divide our input as in the stream of linear line segments. And so these line segments, with by combining these line segments, we can construct the whole time series data. Starting with the sparse PCA algorithm, the compression step, what we do is like we first store some samples, all of the samples, and then at each time step we actually pick some randomly few sensors and store those values of the sensors. In the reconstruction site, what we do is like we take a PCA of the previous few samples and make a dictionary out of that, uh, of those previous sample, and then using that dictionary and the sensors we stored in the compression site, using that we apply the sparse Bayesian learning approach, and we get the we estimate the current sample. So this goes on in loop, and hence the control parameters of this algorithm are the this window size which we take for the PCA and we store at the beginning, and the number of sensors we store at each sample. So the next is we showing the bounded error piecewise linear approximation, which we have analyzed. In this part, what in a PLA, what we happens like we actually approximate the whole time series data as a combination of linear segments. So in one of the way of PLA is the bounded error piecewise linear approximation, where the line segments are extended uh, till they actually remain under certain bounds. So we all those line if we have the main graph is this YT, if we reconstruct it using some line segment, those line segments should be in some bounds. Like I'm going to show you in next slide that suppose we in this graph we actually divide our inputs some specific levels. It's you can take it as a ADC. So we start at one point and we create a cone inside the bounds, and from those actually we try to extend those that cone till it remains according to these bounds till the time it does not have any no longer have any point inside that cone. So we actually have this line segment from one point to another, and we store store this line segment. It can be stored it as a y equal to mx plus c, so we can store it as a m and c. So here we don't have to, we will be storing only two values instead of four values. So in case now this plot shows that if we increase the resolution, we can extend our cone, and so we can extend our line segments. So we can be storing about two values instead of five values. Next, I'll be showing the sparse dictionary compression. This is the third algorithm. Here I should be explain some terminologies. So there's one called triplet, where the triplet is some which is a time series uh, which exhibits some irregularities and non-uniformly sampled, noisy or misaligned. It's a basic segment which construct the time series data. Okay. So we actually create a dictionary using some fixed length elementary time trees, and we call them as atoms. So what we do is we take few number of atoms and combine them to get the time series to get that triplet segment. So that's where the sparse representation. So basically we are having sparse approximation of the triplet segment from. So this using that sparse vector we get in dictionary, we stored the sparse vector only. So for this we actually need a dictionary which can be either learned from the data or some expert knowledge, and then using that dictionary we have to find the sparse vector. So to explain the algorithm, so we will be having, let's suppose we have this triplet segment of size n and a dictionary of size q cross k, where k atoms are there, each having q values. So for learning the dictionary from the data, we solve this joint optimization problem, where we first keep theta I as fixed and then solve for d, and then keep d as fixed and solve for theta I iteratively till we get the best d star as a dictionary. So using our uh, some triplet segments as the training points. Now, during the compression, we'll be using that dictionary we got D, and we'll be finding a sparse representation uh, where we have a sparsity constraint of that of sparsity constraint that we won't be using these many atoms. So it can be one, two, or three. I'll be showing their effect in next few slides. So and we use matching pursuit algorithms to find these sparse vector. And so our compression and reconstruction error is the main parameters for the any lossy compression. Here the compression ratio is number of atoms into 2 by triplet length, because this comes from because we actually divide each chunk and have a sparse approximation for that. So the effect of the dictionary is as for like it's how what is the effect of the length of the atom, or basically the number of rows. What are the effect of the number of columns of the dictionary on the MSE? There's no effect of as I will show, that there's no effect of number of columns on the MSE. And what is the effect of training size of data? So here you can see that this is the result. We increases the length atom length. The MSE actually the MSEA actually uh, goes down, sorry, increases as we increase the atom length, and but the compression actually goes down as we increase the atom length because it's in the denominator. So basically, it will decrease the compression. But why the lower size atom length is actually decreasing the MSE is because a small size atom can actually capture the changes rapidly, but the longer atom cannot captures those changes. And here you can see that the number of columns doesn't have any such effect, any much effect on MSE, because what by increasing columns we are basically increasing our search space. So you can see that there's not big effect according to the number of columns. Here I show the as you can see in what is the effect of a training size of data. So if I use like 100, so we have a very high MSE. But as you can see, for it is less for the number of atoms. Like if we are using 8 atoms, like our sparsity, the sparsity is 8, so it has less error. But as we go on increasing our training set of data, our error actually reduces, and using only less number, we can actually have a better MSE. So It means that having a good training size data for the dictionary learning, only few using only few items, we can actually have a much better MSE. So this is the summary of the compression result, where if I show you like for heterogeneous and homogeneous sensors, where heterogeneous means that different sensors are having a different range, and homogeneous sensor means sensors having same range. So like for homogeneous sparse, which they give 25% compression at a MSE of 500, while sparse dictionary learning they give a 20% compression at the 500, and PLA gives a far more better result, like 3% at MSE for sorry 10% compression at the MSE of 46. So where compression percent is basically output by input. So according to these results, the PLA is working much better for a time series data. Okay. So that's all my work. Thank you.